First of all, I'd like to thank Tian and Hongtu for putting together this wonderful workshop. I think this is the smallest workshop I ever attended, but quite stimulating. I enjoy it a lot. I decided to talk about sort of two examples of some of the work we have been doing here. The first one is more like a specific case study, showing how we use some deep learning tool to help solve some or answer some classical statistical problem that is doing some kind of inference for directed graph. And the second is some kind of actually a series of ongoing works, particularly deep brain stimulation that we are working on right now. Both works are in collaboration with Dr. Chen Chuanshi from London School of Economics, who is also here in the audience. And we all know, deep learning is exploding, and we always ask ourselves this question: how shall we deal with it? And another one way to put it is we can ask how deep learning can help our research, and also how our research can help deep learning. This first case study is more about the first question: how to use some deep learning tools, some very flexible, powerful learning tools to facilitate some classical statistical inference problems. As statisticians, biostatisticians, we are always interested in this uncertainty quantification inference. So the particular tool I'm going to mention here today is using this deep generative learning. There have been a number of different methods. This generative adversary network scans, variational autoencoders, more recently diffusion models, and also transformers. What we want to first talk about in this example is how to use deep generative learning to help this testing problem for directed graph. So our target is kind of simple, well formulated. I have a directed graph. I want to know if there is a link, or more particularly if there is a node from a link from node K to node J. So that's kind of the hypothesis we want to test about. The model we are working with, the working model we are using. Oops, sorry. Go back. Yes, thank you. So the working model we are using just some additive noise model. So here we want to say we do not want to only restrict to linear type models over here. Of course, this question, people have been studying this, have been thinking about this for years. Penalized estimation is a quite useful tool to partially answer this question, but at the same time, we also know estimation is not the same as inference. Bayesian network is another very popular solution, but it often suffers from some computational challenges. As a result, the network size is often very limited. And there have been some recent proposals doing inference for DAG, but usually assume linear type associations and also assume RID data. We want to go beyond this a little bit. So we want to actually, already mentioned, do not have to assume linear type associations. And as we were seeing a minute, a big component of this inference for DAG is conditional independence testing. But it is not only conditional independence test. Okay, there's something different. And we want to also work with some kind of time-dependent data. So in particular, our applications come from neuroimaging studies. We have multiple subjects or multiple trials. Each subject, we observe this brain wave type of data, so essentially time series type of data. Okay. So we try to use some deep learning tools to help answer this question. So again, just some very high-level summary, key points, what we have been trying to do. The first observation is, again, this testing problem is closely associated with this conditional independence testing, but however, this conditional set, on one hand, should definitely include the parents of the node J, but it cannot contain any common descendants of the J and K. Okay, that's a very crucial observation. So this observation allows us to use some technique from conditional independent testing to answer our question, but a very important difference is we have to have a good estimate of the DAG structure at the beginning so that we can exclude those common descendants. Second observation here is this is the key component of our test statistic. And then we actually, this H is some kind of transformation function. We use a lot of different transformation functions to improve the power of the test. So in principle, we can just estimate its conditional expectations in this key quantity of the test statistic, which is just a supervised learning problem. However, because we use really a lot of transformation functions, in our experiments we use thousands of transformation functions, the computation is kind of intractable. As a result, this is where this deep generative learning kicks in. So we learn the conditional distribution, and if we can learn this conditional distribution nicely, then we can easily compute these conditional expectations. Okay, this is where this deep generative learning really helps us. Of course, in addition to that, we also use some deep learning tool to learn the DAG structure at the beginning, and we also use some kind of a deep neural network to do this supervised learning task as well, this single conditional expectation. Now, as statisticians, we are always interested in, does this inference, this test really works? We want to make sure the size is well under control, and hopefully it also has nice power. And this is kind of another kind of a key component of this study. So we build this, we construct this test statistic that is doubly robust. And because of that, a very interesting observation here is we are using deep learning methods, which are essentially some kind of non-parametric learning methods. Their convergence rate is slower than the classical root n. However, thanks to this doubly robustness property and some other kind of properties of this test statistic, we show that the test statistic is still able to achieve the root n classical convergence rate, which is very crucial because this would then make sure we can control the size and also has some desirable power property. So essentially what we are doing over here is we are utilizing those deep learning tools as some sort of flexible, non-parametric learners, and then we try to build our test that can still achieve some parametric convergence rate. Okay. And we did this under the sort of asymptotic framework where either the number of subjects diverge or the number of time points diverge. Okay. We apply this to some kind of brain connectivity example, and we made some interesting findings. I think in the interest of time, I just skip this example here. And then, so again, what we have been doing, as I sort of briefly mentioned earlier, just some example showing how we may utilize those highly flexible, highly powerful deep learning tools to help answer some classical statistical questions. We have done a bunch of other related works along this line. For instance, general conditional independent testing problem or testing the Markov property in time series data, which are all kind of very important statistical inference problems. Okay. Now looping back to this more general question, how to embrace deep learning or AI into our statistical research, right? And there are such fast, so many developments in the past few years. But this computational or practical feasibility is also something we need to take into account. People mention like foundational models, those large language models. Unless you have a lot of money, have a lot of GPU, the computation is not trivial at all. So that is also something we need to take into account. Another question we always want to ask is what kind of unique contributions can statisticians, biostatisticians bring to the table, right? I think many of the speakers already gave some good answers here. We used to think, the machine learning or those computer science methods, the black box, so lack of interpretability. We are good at interpretability. We are good at some uncertainty quantification. But I also want to mention that things are changing very quickly. A lot of people in computer science community are also working on this, interpretable deep learning, right? This XAI. So what I feel, I think one thing we can do, partially answer these high-level questions Hong Tu and posed earlier, is I think we really want to do some real impact, real application. So this is my second example. Again, just a high level. This is a series of works we have been doing in the past few years. This deep brain stimulation. This is a very exciting research direction. It's also part of the bigger effort of this brain-computer interface. Okay, so we spent a lot of years talking to the neuroscientists, neurosurgeons on this problem, and we are developing kind of methods, writing papers and proposals. So simply put, what deep brain stimulation is doing is, sounds very fancy, by the way. We open up the skull, so we drill a hole on the skull. We place the electrodes inside the brain. So this is a highly invasive technology. Actually, to make things even more interesting, the position of those electrodes are very, very important. So to make sure we place the electrodes at the right place during the surgery, we have to keep the patients awake. Okay, so the neurosurgeons need to talk, interact with the patients. Okay. It sounds complicated, fancy, but this technology actually has been quite mature. But people are trying to, have been doing right now is, once the electrodes are placed, the physicians assign those kind of control parameters. For instance, how much stimulation to apply to the patient every day, for how long, and what amplitude. So all those parameters are fixed. Okay. Now we feel we want to do this in a more adaptive way, very naturally, because these electrodes can also collect all these neural signals, feedback from the patients. So intuitively, if the patient is having some less severe symptom today, we probably want to apply less stimulation. Or the other way around, we probably want to apply more stimulation. So naturally, if we think of this problem from a methodological perspective, this is a reinforcement learning problem, right? We want to adaptively come up with some optimal strategy to help improve the patient's health outcome. Okay. But then there have been a lot of papers, a lot of new methods, new algorithms on reinforcement learning on one hand. There is this huge demand from neuroscientists, from neurosurgeons on how to do this adaptive deep brain stimulation. And the reality is there's a huge gap. Okay. There are a ton of practical questions. For instance, the reward, we need to observe the reward if we want to do reinforcement learning. But in a lot of those situations, these applications of deep brain stimulation, the reward is not fully observed, or is not even well defined. For instance, in Parkinson, we kind of have some better idea what kind of reward we want to achieve. But for other neurological disorders like depression, we do not even know what is the best reward over here. Another practical challenging over here is this device. We also implant some device into the patient body. So this device is acting like this kind of controller, deciding how much stimulation to apply. But this device is very simple. It is not a computer. It cannot do those fancy deep learning algorithms at all. So we have to do some approximation. So what I want to say here is there are all these practical constraints. So if you want to make real impact, make this thing really useful, some really useful adaptive RL solutions for deep brain stimulation, I think there's a lot of work we need to do, and we can contribute as statisticians, biostatisticians. So we are actually, as I mentioned, doing a number of different projects trying to address many of those practical challenges. And I feel this is, in my opinion, probably a useful way to incorporate deep learning AI into our research. And at the end of the day, I think we all want to kind of advance the science in the end. Okay. I think that's all I want to talk about. Yeah, stop.
I think if you're talking about a human, DBS, relatively simple because you only have one electrode there normally. And so what we are doing at the moment, of course, we put more electrode in. For example, if we want to use sleep at the moment, so how can we say stimulate a different area so you can get sleep at the moment? So that's what we are doing actually. So we are doing this for monkey, for example. So in monkey, we can really insert a multi-electrode in all the brain, and we can control. And that will be really a feedback control task for reinforcement learning. How can you develop the best parameter setting for not one electrode, but a multi-electrode? So for example, so you can sleep at the moment. So that's what we are doing actually for monkey. So we do implement many electrodes there.
You're right, the number of electrodes right now is not very huge, but still we usually implant 4 to 16 electrodes. Yeah, but sure, yeah. But setting that question, that part aside, there are a lot of common challenges. Like another issue, actually, you mentioned that is there are a lot of control parameters, right? How long, how much amplitude, but then where to place those things, a ton of control parameters. It's very difficult to, to experiment with those parameters, especially on human. So that's also a challenge we have to deal with. Yeah, and of course there are all sorts of ethical issues as well, etc. Yeah.
Thank you. Yeah, I just have a quick question. So what I have learned about neuroscience is that the concept of functional segregation and functional integration, right? So so when placing the electrodes, how do we decide and how do we go for a specific location? So if you are targeting a specific function, for example, sleep. So as of now, recently we know that not a specific region is filtered to that, but a track or a network of the regions. So how do we cater that problem in this scenario?
So I think my understanding, your question is how to decide where to position to put the electrodes?
Yeah,
right?
Not just that. I mean, the thing is, like, in order to induce something using deep learning or reinforcement learning, so in different brain regions, in different scenarios, right? Multiple networks, for example, the default mode network in the resting state. What I'm trying to say is, like, not a specific region. A specific region does not do a specific work all the time, right? Mm-hmm. So how do we tackle that in this reinforcement learning scenario?
Okay, yeah. So I think that there's still a lot of open questions there, like in terms of like the positions we were talking about, and this really depends on what kind of disorder we are targeting. For Parkinson, we have much better idea where to position the electrodes. For depression, for instance, for sleep is something we are also working on, try to improve the sleep quality. We have less clear ideas. Yeah, and also like if you think about depression, what do you mean we are really improving the symptoms of depression? It is not actually a clearly or cleanly defined question either. But then deep learning, so again, what we are doing is we try to, first of all, identify those practical challenges, then try to formulate in this framework of reinforcement learning, and then a lot of those deep learning tools, we use it here, there, as some individual components to help, answer some of those questions. Yeah, please.
So these are settings, so this is the type of setting where I would expect to see more MPC, model predictive control, or methods like that. Maybe I could see RL producing some features that the MPC controller might use, but I don't really see RL being used full force. First of all, you're talking about humans, And there is, and as we all know, that MPC, MPC is used all over the world to control like almost everything, cars. But RL or other AI methods can be used to do feature construction and things like, they can be used to assist the MPC. So is that the direction you're thinking of, as more of as an assist? I know it's totally cool to do RL, but I'm a little concerned about
Yes.
online RL in this setting. Yeah, it's.
You're absolutely right. There are a lot of issues with on RL right now. So as a result, it is not widely used in practice yet. So that is part of the things we want to sort of see if we can come up with more practically useful RL solutions. But another direction we're also exploring right now is doing this kind of hybrid version, integrated version of MPC and RL, right? Exactly as you mentioned, MPC is used everywhere, in autonomous driving, it's kind of, DBS and other settings. So we are thinking maybe RL could help bring some additional, either features or some other additional help to the MPC. So that's also one of the directions we're exploring right now.
A quick break right now. I think we should